Good morning. Yes. I have a class, madam, just now in 11 o'clock. 11, I'll be here till, I'll be here in the morning, so you can send them. Yeah, thanks. Okay, so let's start this lecture. This is the second lecture which is being given on metal carbonyls, and uh, I would encourage you to review this and also read some other texts so that you are familiar with the matter from multiple perspectives, because with 1 hour of lecture on metal carbonyls is it's not possible to cover all aspects of metal carbonyls. Now, in the first lecture, okay, let me see if this is, yeah. So in the first lecture, we looked at some of the special properties of metal carbonyls. We talked about various unique features and compared them with Werner complexes, because those are the complexes which are most common in inorganic chemistry, in transition metal chemistry. And we compared it with them. So what we noted was that there are several features which are unique to these complexes, and we said that any model of bonding that we discuss or that we come up with should account for all these factors in addition to whatever else that might come up later on. So one very important factor that we looked at was the bond distances, which seemed to indicate that there was multiple bonding between iron and carbon, and it is not just a simple covalent bond, which would have required a bond distance of, for example, 2.1, whereas what we observed was significantly smaller. And we also noted that the CO bond length was slightly elongated, although not much, but in iron carbonyl it is very slightly elongated. I have to re-emphasize the fact that, once again, I emphasize the fact that spectroscopy, especially infrared spectroscopy, is extremely useful as far as organometallic carbonyl complexes go. The best model for bonding is the so-called dative bonding, or the give and take of electrons between metals and carbon monoxide. Carbon monoxide gives a pair of electrons from its HOMO, the highest occupied molecular orbital of CO, to an empty metal orbital. And the metal in turn gives from its HOMO, which turns out to be, in an octahedral system, it turns out to be the T2G set of orbitals. From there, it pumps in electrons into the CO pi star. So this kind of give and take was proposed by Dewar, Chatt, and Duncanson. So it's called the DCD model of bonding. And it's summarized in this picture, which gives you an idea of both the sigma bond. The sigma bond is where the carbon monoxide gives electron density into the metal, and the electron density flow is in this direction, whereas in the pi bond, the electron density flow is in the opposite direction. So it is a combination of two bonds. So there is pi bonding and there is sigma bonding. We call this pi bonding only because if you rotate it around this axis, the overlap between the metal and the ligand orbitals will be disrupted. So the phase of these two are unique, unlike this one, where whatever amount of rotation that you might think of, nothing would happen to this bond. So here, unlike the sigma bond, you have a phase change, and so you would end up with loss in bonding as you rotate the metal complex. Now, I think I've covered everything, but then we have studied that it is, or we have learned that it is a combination of two bonds. We have really not established the fact that it is synergistic bonding, and I'm sure you've heard of this term, synergistic bonding. It is intuitively obvious that if one of them is strong, it will strengthen the other also. Why? Because if my sigma bond is strong, my metal carbon bond length will decrease. Okay, if my sigma bond is strong, this is going to decrease. If this decreases, then overlap between the two species is going to improve. Overlap is going to improve. So this is something that will go in a synergistic fashion. But we really, at this point, we really do not have any proof that this is the case. So let's keep going. One reason why we think that it is synergistic is because of the way in which the charge on the metal or the oxidation state of the metal affects these carbon monoxide stretching frequencies. So here I have pictured for you a zero valent, a uni-negative, and a di-negative species. And you see that the stretching frequency is decreasing in this order. So the more negative the more negative, the lower the stretching frequency. This has a lower stretching frequency because the pi star is populated with more electron density. Pi star electron density is more. So this is something that you can explain in terms of both overlap and also in terms of the electronegativity of the system, because if I have a negatively charged metal atom, it's not going to hold the outermost valence electrons close to itself. The electron cloud will expand. The expansion of the electron cloud will lead to a better overlap between the metal T2G orbitals. The T2G orbitals are going to be much larger when you have a larger negative charge on the metal, and so this will be happier to push electron density, or better overlap will be there between the carbon monoxide and the oxygen. Carbon monoxide, carbon and the metal. So this overlap is going to be much better when you have a negative charge on the metal. So this is explainable, and that's what I have already here. I'm sorry, I shouldn't have drawn this extra lobes. So here I have pictured for you a positively charged metal atom, M and plus, where the charge is positive. Then when I have a positive charge, the orbitals will be pulled closer to the nucleus. The electron in a d orbital will be pulled closer to the nucleus when I have a positive charge. When I have a negative charge, I have a larger orbital. When I have a positive charge, I have a smaller orbital. The orbital comes closer to the nucleus. So this will lead to poorer overlap. So the population of the pi star is going to be less in this case, less pi star electron density, and so the stretching frequency is higher, because if you populate the pi star, it's going to weaken the CO bond. If you depopulate it, or if it is empty, then it's going to behave more like the CO triple bonded system that it is in the isolated state. So remember that the isolated state, the carbon monoxide has got a stretching frequency of 2143. So all those stretching frequencies were less. Now, I already explained to you that the carbon end of the carbon monoxide is the one which has got the highest occupied molecular orbital. Now, there is one more reason why the carbon end is bound to the metal. So I have already given you two reasons. One is the HOMO overlap between the carbon monoxide and the metal is much better. The forward bonding, so-called forward bonding, ligand to metal, is better. Secondly, the acceptor interaction between the metal giving electron density into is better, because the pi star has got more contribution from the carbon. Now, there is one more reason why it is better, and that is it is the nature of the pi orbitals on the carbon monoxide. The pi interaction between the carbon monoxide, or the pi orbital on carbon monoxide, and the T2G have got the same symmetry when you look at them from the metal's perspective. By that I mean, if I look at a metal which is facing a carbon monoxide, the carbon monoxide will have a p orbital. And if it's facing a pi orbital or a pi star orbital, it will still see the same p orbital on the carbon end. So as a result, I shouldn't say it is a symmetry is the same, but the phase of the two lobes that are being seen by the metal is going to be the same whether it is a pi or a pi star. So what happens is, this interaction has got a filled orbital, filled carbon monoxide orbital. Pi is filled, and that is going to face the T2G set, and that is also filled. In the case of hexachromium carbonyl, for example, the T2G is going to be filled with 6 electrons. So what happens is this is going to be a destabilizing interaction. Thankfully, this overlap is small, again for the same reason. In the pi orbital, where it is a bonding orbital, oxygen contributes more, being the more electronegative species. Oxygen contributes more and carbon contributes less to the bonding orbital. And this is something that we saw in the first. And because this secondary interaction is destabilizing, the secondary interaction is actually destabilizing. This is the reason why we need to minimize it. And we are automatically minimizing it by putting the carbon end next to the metal. So in fact, there are 3 good reasons why we have carbon bonded to metal through the carbon monoxide. The carbon monoxide is bound to through the carbon end of the carbon monoxide. So until this point, we have used only 1 or 2 examples to derive the principles that we have shown here. Ideally, we should not jump to conclusions by just looking at 1 or 2 complexes. We should look at a large number of complexes and see whether this is a pattern that is followed or whether this is an exception. It's true that I have shown you 5 different complexes in the previous slide, 2 negative and 2 positive, and 1 zero-valent species. But there are a lot more complexes, and so it is possible that we can use a better analogy. In fact, metal carbonyls, we have thousands of complexes. So this is exactly what somebody did. This is a person called Trevor Hambley, and this person did what is called database analysis of transition metal carbonyl bond lengths. So they got some very useful insights, and I will share for you some points from this. The full paper will be uploaded in your team's website so that you can go through it. But let me just give you a few insights from this. First of all, as you increase the population in the pi star, the CO bond weakens. So the bond between carbon and oxygen is going to keep elongating as you shorten the metal carbon bond. Metal carbon bond comes closer, there's going to be better back bonding. Better back bonding, the CO bond length is going to increase. So that's exactly what you would expect if I plot the MO molybdenum carbon bond length and the carbon oxygen bond length in a series of molybdenum carbonyl complexes. Now, if I take MoCO6, there are 6 MoC distances and 6 CO distances. Now imagine 1,000 complexes. So there will be thousands of carbon oxygen distances and thousands of carbon distances. What they have done is they have plotted everything using a computer program. They have gone through the database of crystal structures and analyzed all of them, and you get a scatter plot. Now, if you take the average, what they found was that if they take the average in each complex independently, that means if I take complex A, I have 6 metal carbon bonds and 6 carbon oxygen bonds. I take the average within that complex, in that complex, and then make a point. Then that average falls in a very nice straight line. Not too bad. It's almost a straight line. I shouldn't say it's a straight line. It's almost a straight line. Whereas if you take the scatter, it is take a scatter plot, it is a lot more spread out in this region. But notice this axis is a lot more compressed. The y-axis is a lot more compressed compared to the x-axis. X-axis is expanded out from all the way from 1.8 to 2.2. whereas this is only 0.35 angstroms. This is okay. This is also not too bad, but it is more. But it is 0.4 angstroms. Okay, and it is spread out. But you see that there is a nice relationship between the two, just as you would expect. So what we are saying is not an isolated phenomenon. It's not just valuable for, say, 6 metal carbonyl compounds. It is valuable whenever there is a metal carbonyl compound. This inverse relationship is holding good. You should expect a reasonable inverse relationship. Not only that, if I take a 3D element, the bond distances are shorter. Metal carbon bond distances are shorter. So this graph gives you the relationship between 3D and 4D. It turns out that after 4D, the 5D transition element size is not going to be very different from the 4D. That's due to the lanthanide contraction. So you have 4D and 5D coming almost together. You have a reasonably consistent relationship which you observe for 4D and 5D, whereas for 3D it is similar, but it is shifted to the in this direction. So what we are seeing is a very significant relationship between carbon-oxygen bond length and metal-carbon bond length. This seems to suggest that in fact there is whenever there is a shortening of one bond, the other one is lengthened, and so there seems to be a give and take which is reasonably synergistic. Now I will give you some more information about being synergistic, but let's proceed further. What you find in this almost straight line that I saw, that there are clearly 3 different regions in this graph. One region is where you have a reasonable flat portion, which is like a straight line. This is the straight line that we saw, which I was emphasizing all along. But if you look at the ends, what you find is that there are 2 regions where the slope is different. It is this region and this region that I'm talking about. The 2 ends, the slope seems to be different. Here, if you take the carbon-oxygen in the gas phase, you find that carbon-oxygen will have a bond distance corresponding to 1.12 something, and that's marked with this dotted line, which I have made it red right now, where you have no interaction with the metal. So that's the free carbon-oxygen bond length. And you find that in some cases, the carbon-oxygen bond length is in fact decreased from what you expect. And in some cases, it is expanded or increased more than what you expect from the simple bonding that you have, the bonding pattern that you've been talking about. So if one assumes, it's just a qualitative argument, but it makes a lot of sense, that if you assume that as I remove the metal away from the carbon monoxide, the overlap is going to be less and less. And the pi overlap is going to fall away faster than the sigma overlap. So in this end, you have poor sigma. Here you have a poorer sigma bond, but the pi bond is virtually non-existent. So this 6% is coming from poor sigma, but practically no pi bond. Here I have very strong, very good sigma bond at good sigma bond and good pi bond. And this pi bond is now very strong. So that is why the 4% of the complexes, where probably there is a delta negative charge on the metal, you have very short metal carbon bond distances, and you also have very long carbon oxygen bond lengths. So the increase in the CO bond length is much greater at this end. Here, I have even a shortening of the CO bond length, what you do not expect. And you also find that there is probably only a sigma bond, no pi bond is present because the metal has moved away from the carbon monoxide. So this is what they observed from the database analysis. Now, in the last class itself, some of you were asking me, why are there other effects apart from the reduction in the CO bond order? Now, the fact is, there has been a theory, which I will discuss shortly, that the two effects are in fact working in opposite directions. This has been a major debate, and we will see how the debate has helped chemistry understand the whole phenomenon a little better. When you have pi bonding, we said that the donation of electron density results in reduction of the CO bond order. In sigma bond, we have not made any comment. It depends on the nature of the sigma bond. This is the carbon monoxide. We have a lone pair. In fact, we have a lone pair on this end also. And the metal is accepting electron density. But this is notice that even while saying this, I said that this is a lone pair. What I'm implying is that it's not involved in bonding. If it's not involved in bonding, then it shouldn't matter whether I'm donating it to the metal or not. It should not affect the CO bond order. But we know that it is a molecular orbital. That means that although it is localized on carbon, there is some influence from the oxygen. So let's take a look at the CO sigma bond. But before I do that, I have to one more thing. I'm sorry, I jumped the gun. I should have explained this particular aspect first. And that is, pi bonding is shared by the trans ligand. So very often you have significant effects from the trans ligand. And I will just briefly touch upon that before I talk about the sigma bond. Okay, electron donation ability of the metal is going to be affected by other ligands on the metal. So you have ML5 carbon monoxide. So this L5 is going to affect how effectively the metal can push electron density into the carbon monoxide. And I want to submit to you today that it is the trans bond, the bond in the trans geometry, whenever there is a trans geometry, which is going to make a significant effect. Now, if we look at the T2G6 set of orbitals, notice that each one of these ligands is lying along the axis. They are lying along the plus x, plus y plus z minus z axis. And so, if I have one ligand on the plus x axis, the same T2G orbital is involved in pi bonding with the other ligand on the minus x axis also. It is the same orbital. So if I'm pushing electron density from the metal to the pi star on one ligand, the carbon monoxide on the trans geometry, that is also competing with the same T2G orbital. It is the same T2G orbital that is being shared by ligand 1 and ligand 2, L1 and L2 being trans to each other. So if I have a ligand which withdraws electron density from this T2G orbital, then the ability of the metal to give electron density into the pi star orbital is going to decrease. So if that happens, then the stretching frequency will also change. So do we have any proof for this? It is there. I will show you in a few minutes. On the other hand, if I have a pi bond, if I have a ligand L2 which can push electron density to the T2G, then this electron density will be pushed back into the CO, and then the pi star occupancy will increase. I said that it will decrease. The metal to ligand pi star pumping in of electron density from metal to ligand is going to decrease. So this is going to be less. In this case, it is going to increase. So you will both observe a change in the stretching frequency, and you will also observe a change in the bond distances. So best thing to look at is to look at some structural evidence. I have for you here an iridium complex in which there are two carbon monoxides bound to the same iridium. Now they are cis-related to each other, and in the transposition to each of these carbon monoxides, I am having another ligand which is not similar. So in one case I have a chloride, Cl, and the other case I have a carbene. This is a carbene, CnR2. There is a lone pair here sitting here, which is giving electron density. Now, just like a carbon monoxide, a carbene can also have a pi ligand, which is empty, and this is a poor pi acceptor compared to carbon monoxide. So this is a poor pi acceptor, and if I look at the distances, I have written out the distances. Let me see, 1.87. This is the distance, 1.87, and this distance is 1.07 angstroms. Okay, so trans to the chlorine, what you have is a distance of 1.87 angstroms and 1.07 angstroms. And when you take the ligand which is trans to the carbene, which is a very good electron donor compared to the chloride, then I have a distance of 1.89 and 1.131. Notice that this CO distance and this CO distance, these two are indicative of how much pi star population is there. The pi star population trans to the chloride seems to be much larger. Why? Because chloride is pumping in electron density into the iridium dx. If I look at it as a d, this is the x-axis. That means the chloride CO axis is x-axis. The dxz axis will be involved, and then the pi star will be populated. And so I have. Sorry, I think I reversed the argument. Chloride is okay. Chloride has got two effects. I have both a pi star donation as well as an electron withdrawing capacity. So I do have a difference here. This is this is the donor. This is the donor. Okay, this is the donor, and I have opposite the donor, I have a weakening of the CO bond. Sorry about the mistake that I made. This is a complicated, slightly complicated example because I have chloride, which is it's possible for the chloride to push in electron density to through the lone pair also. So there is a complication. I think I took a more complicated example first. In this example, you have multiple effects operating, but what you see is that in the chloride, you have a longer MC, shorter MC bond, and as a result, more population on the pi star. Here, I have only the sigma, no pi, only the sigma, no pi donation. Okay, so as a result, this distance is longer, This distance is longer and this distance is shorter. Okay, so you have multiple effects here. I will, let's keep this example. Let's go to a different example where I have only a sigma bond. So that confusion will not be there. This is a rhodium example where I have amine, and the amine doesn't have a pi star, only sigma donor, no pi at all. So there you had a slight complication from a pi accepting competing ligand. So here the distances are very clear. This is shorter and this is longer. Carbon monoxide trans to the chloride is much more strongly bound than the carbon monoxide which is trans to the pure sigma donor. This is a pure sigma donor. No pi. And so what happens is this distance is longer. This is 2.16. I'm comparing that with 1.83. You can see that the previous example was a poor example where I have competing effects. So here I have a very clear distinction between the two. The chloride is both a pi donor and a sigma donor, whereas the amine is only a sigma donor. So what I'm having here is a very clear difference between the two species. I have short metal carbon bond distance opposite the chloride, and I have a longer metal carbon bond distance opposite the sigma donor and no pi donor. And so this bond is really short. This bond is 1.6 angstroms, and so this is much longer. The 1.6 angstroms long. So this is much longer, 1.16 angstroms long. So this is much longer than the carbon monoxide, which is trans to the amine. Okay, so the chloride, of course, has got the right pi orbital in order to pump in electron density into the T2G, which in turn can pump in electron density into the carbon monoxide. So structurally, if you look at many different examples, you will find that this is true. Unless you have complications like the way in which we have shown here. Here, you have a complication from the pi effects of the, this is a poor pi acceptor. So it has a pi as well as a sigma donor ability. Whereas here there is no pi donation. When you have pi donation or pi acceptance, you have competition between the two species. Now, let me give you some more chemical evidence. The chemical evidence that we see is very significant. If I take carbon monoxide complexes and do a substitution, suppose I take a trimethylamine ligand, two equivalents of trimethylamine can give me, so CrCO4 L2. This can be both a cis and a trans compound. If I do more than two, I can have CrCO3 L3, and this again can be FAC or MER. Here it can be cis or trans. Now, depending on the ability of the ligand to compete with carbon monoxide. Suppose it doesn't compete with carbon monoxide for bonding. It's a much weaker bond. In fact, the substitution occurs. In other words, the complex always forms a FAC isomer. So the FAC isomer has got all the ligands, all the incoming ligands trans to the carbon monoxide. Why? Because carbon monoxide is an extremely good pi acceptor, and it would like to maximize the amount of pi bonding that is there in the metal complex. anything that is a weak pi acceptor on the trans geometry is better than having a carbon monoxide which will compete with the pi electron density. So here I have for you 4 complexes. All 4 of them are phosphorus-based ligands, but PF3 is a very good pi acceptor, almost as good as carbon monoxide, but it is not as good as carbon monoxide. So you're able to make PF3 complexes, and what you find is that all of them are in fact FAC isomers. And if you look at the stretching frequency, the stretching frequency keeps decreasing. For the carbon monoxide, the stretching frequency keeps decreasing as the electron donor ability of the phosphorus increases. So PF3 is a poor electron donor. Then the stretching frequency is high, whereas when you have PME3, which is a very good electron donor, then the stretching frequency is very low. So just comparing the stretching frequencies, you can see that the pi effects have been shared by the carbon monoxide and the phosphorus ligands. But more importantly, it is only the FAC isomer that is formed when I try to do a substitution reaction. So similarly, if I do a dye substitution, it's only the cis complex which is formed. The trans complex is not favored. So if I plot the electronegativity of the substituent versus the stretching frequency, I get a similar reasonable relationship that I have shown here. So here I have for you this PF3, PCl3, POET3, PET, etc. And I find that there is a reasonable relationship between the trans ligand and the carbon monoxide stretching frequency, which also seems to suggest that it can be because of this poorer pi acceptor property of the trans ligand, or the absence of the pi acceptor property of the trans ligand. So right now what we have said is that the pi acidity, by which I mean that the acceptor ability of the carbon monoxide for electron density, the acceptor ability of the pi star orbital in carbon monoxide is known as the pi acidity, is what is making the metal carbon bond have a double bond character. So this seems to increase pi acidity. Pi acidity of the carbon monoxide is higher in complexes where you have a ligand which can donate more electron density, or you have a negative oxidation state. You either have a negative oxidation state, or you have a ligand in the trans geometry which is capable of donating electron density. It should at least be a weaker pi acid ligand, or it should be a pi donor if I want to maximize pi bonding. So pi bonding is increased by the charge on the metal. It's also increased by the pi donor ability of the trans ligand. The pi donor ability of the trans ligand. So based on whatever we have said right now, you should be able to arrange the carbon monoxide stretching frequency as a function of the charge on the metal. You can also predict relative bond distance changes, unless if it is complicated like the one that we just saw. But you can at least rationalize the metal carbon bond distances based on the bond distances that you, the electron donor ability or the electron acceptor ability of the trans ligand. Okay, so so far we have looked at carbon monoxide complexes, which are, you have to compare apples and apples, not apples and mangoes. So by which I mean that if I am comparing like the 4 coordinated complexes, square planar complexes that I showed to you, you should compare only square planar complexes. If I have tetrahedral complexes like the one that I'm showing you right now, nickel tetracarbonyl, then you restrict your discussion to nickel tetracarbonyl. If I start comparing the octahedral complex with the tetrahedral complex, I may not get a similar a reasonable answer because the interaction of the ligands are going to be different. Now, let's take a look at some of the things which do not form metal carbonyls. For example, zinc 2 plus is a D10 element just like nickel, but it does not form a similar complex. It may not, it is probably a matter of time, people might make it, but even if it does, the interaction between the carbon monoxide and the metal is going to be very weak. Why? Because of the positive charge, the d orbitals will be shrunk and the extent of donation will be very poor. It's not going to be as good as the nickel 0. In fact, it took a long time before a person called Strauss. Strauss discovered several complexes which had metal 2 plus oxidation state and interacting with carbon monoxide. I have shown for you 2 here, and these 2 systems have got high stretching frequencies. Now, if we have very high stretching frequencies, not only that, it is more than 2143 centimeter minus 1. So you have an increase in the stretching frequency. That means CO bond order is greater than what is there in carbon monoxide. If I say that there is no pi bonding in these complexes, then I should not get an increase in the stretching frequency. Pi bonding only populated the pi star orbitals. So when I'm having a positive charge, the pi star orbital will not be populated. That's fine. But then why is the stretching frequency going up? That's something that we need to worry about. But just a brief comment about these compounds. Many of them are difficult to make because they are positively charged. I need a fairly large anion to stabilize the solid structure. Now, of course, solution structures are not going to be affected by the size of the anion. But then what happens in solution is that the rate at which they undergo reactions is much faster. If it is in a solid, if it is a solid, then what happens is the solid is to a certain extent protected by the lattice. You have fewer molecules on the surface, so the inside molecules are protected. So solids are much more stable compared to solutions or liquids, and they're more reactive towards oxygen. These molecules are extremely susceptible to nucleophilic attacks. So any small amount of water or oxygen is also a good nucleophile when you compare it with species like this. So they will all start reacting with this. As a result, you need to stabilize it in the solid state, and it was only Strauss who made these large anions, very large anions, to stabilize these molecules. And he prepared several of them, and all of them had higher stretching frequencies than the carbon monoxide. So one reason that was given was that the 5 sigma orbital is in fact anti-bonding. If it is anti-bonding, then one way to explain this is donation of electron density from the carbon monoxide to the metal would increase the bonding nature between carbon and oxygen. So carbon and oxygen bonding would be improved if I increase the extent of electron donation from the carbon monoxide to the metal. So this was explanation that was given, and the explanation was that the HOMO, which is what we have been calling as the 3 sigma orbital on carbon monoxide, is slightly antibonding. I'll just briefly show you the picture. If I look at the picture, this is my 1 sigma, this is my 2 sigma, this is my 3 sigma. But unfortunately, if you look at the 3 sigma, there is a lobe in between the carbon and the oxygen. This is the oxygen end. Here, somewhere here is the carbon buried inside. It's shown here. So this is the orientation. So what you have is a lobe which is in between the carbon and oxygen. So some amount of electron density is there. So any buildup of electron density between the carbon and oxygen would lead to a bonding interaction. So this is very controversial. Why is it that you are pulling out electron density from here and you have increase in stretching frequency? Whereas if I look at the nature of 3 sigma, this simple, of course, this is a simple calculation, but even this calculation seems to indicate that there is some electron density build up between carbon and oxygen. In fact, what you should compare is, you should compare it relative to the atomic populations. All those things have been done, and the results are very much dependent on the type of basis sets you use, type of calculations you do, and so there is no consensus. And what I will show you in the next class is that I will show you why this is in fact a controversy and what was done in order to solve this controversy. But let me briefly stop here and ask for any questions. Otherwise, I'll go to the next section. Any questions at this stage? Okay, if there are no questions, I will just show you. These are things which we discussed. And here are the 2 complexes that I initially introduced to you. What I have to emphasize is that carbon monoxide can be ionized. Carbon monoxide can be ionized to CO+. The stretching frequency of that species also goes up, which means if you remove an electron from the highest occupied molecular orbital of carbon monoxide, stretching frequency will go up. That's exactly what has happened in this compound. So please ignore the statement. We will discuss that. Is my screen visible?
Yes, yes, sir.
Okay, fine. So this is a slide which just tells you how, if I ionize carbon monoxide, I have an increase in the stretching frequencies. And if I ionize carbon monoxide, the CO bond distance also goes down, which means the carbon-oxygen bond strength is improved. Now, these factors are suggestive of anti-bonding character for the highest occupied molecular orbital in carbon monoxide. But as I told you, this is in fact a bit controversial, because if you look at the picture that I just showed you, it's not so obvious. The fact is there are 2 nodes in between the carbon and the oxygen and buildup of electron density. So that's why it's very complicated. CO plus, the bond distance is 1.15 angstroms. Okay, so this is in fact shorter than free CO, which is 1.12. So it's slightly, these are microwave studies, so they are fairly accurate. Okay. Now we have gone through this. Now I have to look at the Fenske Hall paper, was in fact published in 1972. What they did was they looked at 24 different complexes. All of them were D6 systems. I told you, you should compare apples and apples. So they did exactly that. They looked at D6 systems. They looked at several compounds which were octahedral in nature with 1 or 2 halides. What happens when you have a halide? The halogen is electronegative, so it's going to pull electron density from the metal and leave the metal partially positively charged. So when there is a positive charge on the metal, then the increasing positive charge is going to affect the carbon monoxide stretching frequency. It will do that on the carbon monoxide which is trans to the ligand significantly. Now, there are some defects in the study, and one of the defects or criticisms that can be made is not all cases did they have bond distances, but they estimated bond distances from related systems. That's what a computational chemist will do. Now, let's continue, see what they did. They tried to explain everything in terms of the DCD model. They said that both phi sigma and 2 pi is actually the pi star. Okay, it just depends on what school of theory you come from. The simple organic chemists would say sigma, sigma star, pi star, whereas the computational chemist will always count the number and the symmetry. So they will just count it as 1 pi, 2 pi, 3 pi, 4 pi, etc. And here it is 2 pi is the same as the pi star. Okay, so here is the occupancies that they calculated for these compounds. This is a computational study. Fenske and Hall are 2 computational chemists. And what they found, I'm just going to point out one thing, which they also point out in the paper. The force constant between the carbon and oxygen. This is the force constant between carbon and oxygen. This force constant is almost the same for these 2 complexes. But if you look at the pi star occupancy, the pi star occupancy is different. But if you look at the sigma occupancies, the sigma occupancy is also different. When one is compensating for the other. When this the 5 sigma occupancy is less, then this is 5 sigma on carbon monoxide. This is on CO. What is left behind on carbon monoxide? Remember, in free carbon monoxide, this occupancy should have been 2 electrons. So 1.293 means 0.7 has been given to the carbon monoxide. Okay. Now, what you find is in the 5 sigma, there is a depletion of electron density. When that is less, for example, in the manganese compound, the depletion is less, then the pi star occupancy is also less. When this depletion is more, in the case of iron, the depletion is more. 2 minus 1.293 is what has gone out. Then the pi star occupancy is also higher. Now, this clearly tells you that these 2 factors are synergistic. And what it's doing is that it is compensating for the CO stretching frequency. So in other words, the CO stretching frequency, there are 2 factors which are operating, both operating in opposite directions. Pi star occupancy is going to decrease the stretching frequency. The sigma is going to increase. Sigma donation is going to increase. So these 2 are compensating, and so the net stretching frequency is almost the same. So this is what they discovered from the study of the stretching frequency. So this nicely explains, one is a sigma donation, and that sigma donation is in fact sufficient to improve the stretching frequency, so it must be antibonding in character. That was their conclusion. Now, what they could do was that they could draw a very nice linear relationship between the sum of the two populations and the stretching frequency converted to force constants. Force constant and stretching frequency are related by a simple relationship. If you do some approximations, that is an approximation, but you can relate it as nu equals 1 by 2 pi into root of k by mu, right? So that kind of a relationship is what they used, and they derived the stretching frequency, they derived the force constant and plotted it against the effective occupation, and that's what I'm showing you here. And they got a nice straight line. This straight line had a nice coefficient also. They had a nice regression coefficient also, regression constant also. So it seemed to be a very nice relationship between just the phi sigma depletion and the pi star occupancy. Phi sigma depletion and pi star occupancy. So this is the equation that they derived. So I will continue from this in the next class, because if I start the next section, it will become incomplete. So, but this gives you an idea that it is possible to have a very nice relationship between these 24 systems. That's the complexes that they have observed, and they have got this very nice relationship that we're talking about. I'll stop here. If I have any questions, I will.
Sir, in the rhodium Cl complex which you have shown, that Cl has a pi donation effect, whereas it can also withdraw electrons because it's electronegativity, right?
You're talking about the previous set of transparencies, right?
Yeah.
Yeah.
So it can also withdraw electrons by the by the electron withdrawing effect due to its electronegativity. So that would create a del positive charge on the metal, right?
Yeah.
So it should again increase the CO frequency.
That's why I said that example is a bit complicated, and you can see that if you look at a series of complexes like we are seeing right now, there is a very clear relationship that you can derive for the stretching frequency and the occupancies. Occupancies are calculated. Stretching frequencies are what they observe for these complexes. So there is a combination of two factors. One is the sigma depletion, the carbon monoxide depletion of electron density. The other is the pi star occupancy.
Okay.
So your question is that there is a competing effect in chlorine.
Yeah, competing effect. Yeah, which would predominate when
there is. That's why hand waving arguments are difficult to make when it comes to so once again, when it comes to the so the arguments in the case of these two systems, you're able to see the slide, the rhodium and the iridium.
Yeah.
Yeah. So here there is a chlorine has got an electron withdrawing effect, all right, but it's a sigma donor, and it is at the same time it's also a pi donor. Okay, so in fact it should have strengthened the bond distance even more. I would have expected it to strengthen the bond distance even more, but here because of the electron withdrawing capacity also, it seems to be balanced out. Similarly, this is also a complicated example in the sense that it is a very good sigma donor and a poor pi acceptor. So both are there.
So due to this competitive effect, the bond length is not decreasing as much
Yeah,
as
it's
it is
not
expected.
decreasing as much as you would expect. I should have put this example first. Here, it is very straightforward. Here, it is an amine and a chloride, and the amine has got no pi effect. There is absolutely no pi. So you only have sigma donation. Okay, when you have only sigma donation, here you have both sigma and pi, and the pi donation results in a strong bond opposite and a weakening of occupancy is in fact significantly higher in this carbon monoxide compared to the pi star occupancy in this carbon monoxide.
And so does the electron withdrawing effect can cause the depletion of the sigma electron density of the carbonyl from the carbonyl group of the trans ligand? Electron withdrawing effect of a trans ligand, can it cause the depletion of the sigma electron density from the carbonyl group?
Yeah, the effect is what you're this. If I have electropositive, this is improved.
Okay, yeah, the sigma.
Okay. Any other question?
Sir,
Yeah.
like how does the strength of the sigma donation of the trans ligand affect the sigma bond of our ligand of observation? Like if I have a Me, or like if I have a methyl ligand opposite to the CO group, trans to the CO group, how would that affect the sigma bond of the CO? Like it will increase the electron density on the metal center, so the pi donation of the metal would increase. But how will the effect on the sigma bond in the of the CO bond have change?
Yeah, unfortunately, the sigma bond is also shared. So if I look at the sigma bond, that sigma bond is also shared. So as a result, these are, if you are pumping an electron density from the trans ligand into the sigma bond, the same orbital is also an acceptor orbital for the trans CO, right?
Yes, sir.
Yeah, so they're all shared effects. I mean, you cannot isolate. You can isolate sigma and pi to a certain extent, but in fact, trans and trans ligand is the strongest interaction. The cis ligand also plays a part because the net electron withdrawing capacity of the metal is going to change if it is having other ligands which are electron donating, right? So this is it's not just the trans ligand has the most, that's what I should say.
So ideally, if we would want to have ideally we should have like strong cis sigma ligands and like good trans pi donation ligands for a good MC bond of MCO.
Yeah, if I see, ultimately you have to optimize the system so that the stability of the whole system becomes high. If you strengthen one at the expense of the other, you're not going to gain much. Am I? Is that clear? If I
Yes,
just,
sir.
yeah, if I'm going to weaken one bond and strengthen something else, that's not going to help too much. If I find the optimum distance where all the metal ligand bonds are strengthened and the maximum bond energy is achieved, that is the ideal situation.
Yes, sir.
Okay, so we'll meet on Friday and I'll conclude this section. So I think we'll stop here. Yeah.